Hi, my name is Azra Hafiz, your TiNKA educator. Welcome to TiNKA Lepot series. Before we begin, don't forget to follow our social media, press the like button and follow Facebook and Instagram on the link below. Let's begin. So the other day we've already talked about how the latent heat, specific latent heat of fusion and specific latent heat of vaporization occur, and we defined the formula as well, the definition of the term. But today we're going to take a deeper look on the graph that I've shown you in the previous class. So following the topic of heat, what we see is that in any kind of substance, regardless whether it's metal, non-metal, whether it's water, whether it's a complex substance or a simple substance, they will obey this graph, where within the graph what we'll see is that it changes state from solid to liquid to gas. And yes, there are certain substances that do not have liquid as a state of matter, but they still obey somewhat similar graph where the solid mixed with solid gas and straight to gas. And the temperature of gas will keep on increasing regardless of what your temperature is without changing any form. Where within these three stages, the solid, the liquid, and the gas, what you will see here is that the increase in heat energy will increase the kinetic energy of particles. Similar as what you've learned in your chemistry as well as in Form 1, Form 2, Form 3, where we learned that the change of energy from one form to another, for this case, they change from heat energy to kinetic energy. We can see that the solid particle, for example, even though they are next to one another, they start to vibrate faster and faster between themselves. And this vibration may create a bigger vibration that can change the natural state of the matter. That's why when you start to heat up metallic objects, what you can see is that sometimes even if you use your pot, for example, you can see that the metal will start to vibrate on top of the stove. The reason being is because all of these particles start to gain kinetic energy, they become very excited and they start to cause this oscillation that leads to vibration. Now the same thing that is happening with the liquid and the gas. Increase in the temperature, where on this side we have our temperature, leads to increase in heat energy, and this increase in heat energy will cause the particle to gain more kinetic energy. And here, what you will see is that they will not change any state, they just remain in their state until they reach these two thresholds, the T1, the capital T, and the T2. These two thresholds are the points where you have here, on this side is basically your melting point, and here is where your boiling point is. Now, generally when we are asked about how the graph come about, or they would ask in exam, explain what you see on the graph. So what you say is that from T0 at the beginning of time to T1, the state is solid. Increase of temperature cause the particle to gain kinetic energy until it reach the T capital 1, which is the melting point. And then we talk about the liquid. Liquid state is between T2 to T3. The time is T2 to T3. And here, from your melting point, it moves to your boiling point. The same thing that we'll talk about for gas. T4 onwards, what will happen is that the state of matter is gas and the energy increase in, the particle gain, experience increase in kinetic energy. Now, this is not the main concern in your AC. Your main concern in AC is for the liquid gas state and the solid liquid state. There's a mixture of two states within here. And what we can see here is that in these two states, so we can say at T1 over here, where we have our solid liquid, what happened here is that the particle absorb heat energy to break the bond. So when you have a mixture of solid and liquid, what happens to your particle is that between one particle to another, there are intermolecular forces of attraction that you've already learned in your chemistry. And this intermolecular force of attraction can be either hydrogen bonding, or we can say that for this one, we have the van Waals. Or for some, we can see that there are electrostatic force. And what they do is that the heat energy breaks this bond apart. That's why for some particles, they start to change state from solid to liquid. And some still remain in solid because the heat energy is being absorbed. Here, the temperature does not increase. As energy is used up for breaking of bond. The same thing that is happening within our liquid and gas. You can repeat the same statement for both of them. The only difference is that you change the term from their changing state from solid to liquid, and on this side you can say that it's changing state from liquid to gas. The same phenomenon that is happening, that is explained here, is happening in both phenomena. The only difference is that for this state, we call this as the latent heat of fusion. And on this state, we call this as latent heat of vaporization. And now we're going to talk about the applications of specific heat capacity. Now, when we talk about specific heat capacity, we talk about how much heat energy is needed to change the temperature of a substance by 1 degree Celsius. So what happened here is that we can talk about how fast a food is cooked or how slow food is cooked. Why is this a matter for us? Is because different material have different specific heat capacity, and the different material allow for different type of food to be cooked properly. For example, in Chinese cooking, they prefer to use wok. The reason is because wok, which is made up of steel or aluminium, both of these material has a very low specific heat capacity. And if you've seen a wok before, they are very wide in space. So the area is very big, allowing for more fire to be applied in an area. Due to this very low specific capacity, what happens is the metal itself is also a very, very good conductor. They have high heat transfer rate. So what happens is within your wok, the heat is transferred equally in all directions. And all of this occur in a very short period of time. So when you are cooking your food, what happens is that heat is applied directly to the food, allowing for food to cook fast. Now, here is the problem for the wok itself. Because of the material itself has a very low specific heat capacity, what happens is the entire wok will heat up the moment they are being put on the stove. So, for the wok to be safe for chef to use, is that what they do, they apply handles that has a very high specific heat capacity. And this handle must also have a very high melting point. We don't want the material to melt while the chef is cooking their food. So here, this is the aspect of safety. When you are asked to design your wok, what happens is you increase the surface area. And the reason you increase the area is to allow more food to be cooked, and you can cook food at a very fast rate. The next thing that you can use is you can use materials that has a very low specific capacity. This allows for heat to transfer faster. The next aspect is use the handle that has high specific capacity, allowing for the handle to be cool at all time. And finally, you use materials that have a very high melting point. The reason being, you don't want the handle to melt while the process of cooking is taking place. Now, from the wok, we look at Indian cuisine. Most Indian cuisine, in traditional manner, they use claypot. Now, clay itself is a material that has a very high specific heat capacity. Food cooked in clay are usually cooked at a much longer period of time compared to when you're cooking in a wok. Does that mean that clay is a much better or less better compared to wok? No, they have their own ability and extra traits that allow them to be the perfect usage in cooking. For clay pot, here you have high specific capacity. And this will allow your food to remain warm for a long period of time. And the aspect of safety is not really a concern here, is because of the handle of the clay pot is not directly heated by the fire, so the transfer of heat is much lesser. But for clay pot, one of the concern that you need to know is that clay, when they are heated and cool very fast, they are mostly brittle. They break easily. So what we do with the clay pot is that we use TiNKA pot. And the reason is to prevent breaking. Aside from this, for the clay pot, what you do is that you can use smaller volume. This is done to make it cook faster. And this is the first two application where for the wok and the clay pot explained in the manner of specific heat capacity. The next application for our specific heat capacity is that we can take a look at the engine of a car. Inside the engine of a car, what we can see is that the engine has radiator fan, and we have our radiator fin. And this radiator fin and fan passes through a series of tubes. The air passes through a series of tubes that is connected to the engine. And this series of tubes is basically your cooling system. Now, for the cooling system, what they need to do is that the pipe itself must be made of low specific capacity. This allows for the heat to enter into it faster. And then your pipe must also be made of non-corrosive material, or they resist corrosion. So usually for this we use alloy. You don't want rust within your cooling system because then you will add impurities. And another thing is that this pipe must have a high melting point. Your engine can actually reach temperature beyond 100 degrees Celsius when they are operating like normal basis. Next, we look at the within the cooling system, where the cooling liquid is called coolant. And this coolant has a very high specific heat capacity. What it does is that this high specific heat capacity allow for more heat to be absorbed from the engine. What this does is that it kept the engine at a safe temperature to operate on. When the engine reaches a certain temperature, what happens to the fuel that is injected into the engine is that it combusts at a much higher rate. When your engine is burning fuel at a higher rate, what will happen to your car is that it will start to operate in a very inefficient manner. It produces gases that can be toxic to the environment, for example, carbon monoxide. Now, aside from these two things, we can see here that the fin must be numerous. This fin that is numerous allow for more air to enter and cool the coolant down. How your cooling system works is that this coolant or cooling liquid will come from a tank and move towards your engine. Here, where your engine operates, it releases a series of heat. And this heat are absorbed by your cooling liquid or the coolant before it enters back into the cooling compartment. And this coolant, as it travels through the series of tubes, are being cooled by the radiator fan. The air from the outside, which is having a much lower temperature, is blown to the cooling liquid. This whole system kept your temperature of engine below 90 degrees Celsius. Our engine are not the most efficient equipment out there, but we kept it at a lower temperature so that it can efficient at the maximum output that we can achieve. Done. Now we're going to take a look at the phenomenon of day breeze and night breeze. You might have an experience before when you go to the beach. What happens is that when you enter the water, in the afternoon, the water is very cold. The same thing, if you've tried the water at the sea at night, you can feel that the water in the sea is much warmer compared to the land. What happened here is that it's because of the difference of specific heat capacity between the land and the ocean. Now, we know that the ocean is a very large body of water. And we know that for water itself, even pure water, has a specific heat capacity of 4,200 joules per kilogram per degree Celsius. Just imagine here, you have per kilogram. Imagine a body of water that is limitless. Your ocean are connected from one place to another. Regardless of how long the sun is up, it takes a very long time for the sun to supply all the heat to the water. It takes a very long time for the water to reach a high temperature. Now, this is different for the land itself because your land has a very low specific capacity. So what happened to your land is that as it has a lower specific capacity, it gets heated up first. So the temperature of land is much higher. The increase of temperature on land is much higher. This causes the temperature on the surface of the land to be higher than the temperature on the surface of the ocean. So what happened here is that as the temperature of the soil or the surface of the land is increased, the air on top of the surface is also experiencing increase in temperature because the specific heat capacity of air as compared to the ocean is much lower. So the air gets heated up, and what happens is that the air will move upwards towards the atmosphere. where it will start to get cooled down. As the air gets cooled down, it must travel somewhere. In the upper atmosphere, the air moves towards the sea. Now, as it moves towards the sea, the air gets cooled down. And you can see that the air will start to move towards the ocean. And this create a sense of convection in your air. And this convection creates the wind that will blow to land. That's why we call this as the sea breeze. The day breeze is also called the sea breeze. Now, when the sun starts to sink, you shift from day to night. What will happen here is that the temperature on the land is also shifted. Due to that, the land having a much lower specific heat capacity get cooled down first. As opposed to the ocean, what we can see at the ocean is that the ocean is still warm. This is due to the higher specific heat capacity, causing the ocean to release heat at a much slower rate. They contain more heat energy, so it is releasing heat on the surface at a slower rate. It is still warm. You can still feel the warmth of the ocean up to 2 to 3 a.m. So what happened here is that as your sea water is warmer, the air above the ocean is warmer and rises upward. Now, as it rises upward, similar as how happened in the sea breeze or the day breeze, it get cooled down and move towards the land. And then as it moves towards the land, what happens is that the air in this region has a much lower density, causing the wind to blow from land to sea. And this side, you have your night breeze, or we call this our land breeze. These are the two phenomena that happen in specific heat capacity. And now we're going to talk about the specific latent heat fusion and vaporization application. Now for this topic, our application, there's only one that you need to be concerned of. It is your refrigerator. Now within your refrigerator, have three compartments that you need to be aware of. The first one is called the compressor, the condenser, and the evaporator. What the compressor does is that it compresses the air and change it back to liquid. The condenser allows for the condensation takes place, where it cools down the air that is being compressed. And then the evaporator is when the liquid coolant enters it and changes state from liquid to gas. This whole process happens at the back of your refrigerator, and it allows for your food to be kept at a lower temperature. So what happened is that the evaporator, in this region, your liquid coolant, which has a very high latent heat of vaporization, to absorb the heat in refrigerator. Now, what it does is that when they have a very high latent heat of vaporization, more heat is able to be absorbed from this region. So your liquid is then turned to gas. And we know that this gas has a very high specific heat capacity. So as it travels down towards the compressor, this gas absorbs more heat from the fridge, allowing it to expand. So the gas that is expanding move towards the compressor, where the compressor, what it does is that they compress the air, and as you compress your air, we'll talk about the application of physics law that involve it later. What you will see here is that the volume of the air decrease, and now you have air that is extremely hot. So it moves towards the condenser, where the condenser, similar as how your engine cools down the cooling liquid, it condenses the gas. And here, as it condenses, it turns from gas, they are converted back to liquid. And this liquid will eventually move back to the evaporator, and the whole process will start again. Now, your compressor, they don't just compress the air and decrease the volume. The compressor also cools down the air. Before it is moved towards the condenser to allow condensation to take place. Now, both your evaporator and your compressor are placed in the same region, where it is inside your refrigerator unit. But the condenser are basically a connection that you can see behind your refrigerator. So if, let's say, you take a look behind your refrigerator, you can see a series of tubes moving from down upwards to your fridge unit. Now we're going to take a look at some of our heat laws. So the three heat laws that you will learn in this topic is the Boyle's law, the Charles law, and the Gay-Lussac law. Now I'm going to keep the Gay-Lussac law for a while. We're going to talk about the Boyle's law and the Charles law first. So in Boyle's law, the definition of all three laws are about similar to one another. So please memorize the keyword that you need to put into your definition. For the Boyle's law, for a fixed mass of an absolute gas. Now, this word might be a bit intimidating to you. What it means is that the mass must remain the same. Some gases can change its mass accordingly. But for all of our heat law, the mass of the gas cannot change. And it must be only one type of gas that we know of. It cannot be a mixture of different types of gases, because it might affect how your law operates. So for a fixed mass of an absolute gas, what happened here is that for Boyle's law, pressure is inversely proportional to volume, where temperature is kept constant. So when we look at our Boyle's law, what we see is that it is P1V1 is equals to P2V2. This is a fixed formula, and please memorize this formula. So for the Boyle's law, what we see is that the P and the V is inversely to one another. When we plot the graph of our experiment, what we see is that for our pressure and volume, as the pressure increases, the volume decreases. And this you've already learned in your science subjects when in Form 1, Form 2, Form 3, where we can see for our lung, the pressure within the thoracic cavity decreases, the volume of the lung increases. The volume of the thoracic cavity increases. So they have been working inversely throughout your study of science. So for the Boyle's law experiment, we can do this experiment very easily by using syringe and we inject empty air or inject a gas into a Boyle gauge. So what we can see is that as we inject more volume of gas into this, what happens is that your Boyle gauge eventually decreases. So this is for the Boyle's law. Another thing that we can observe for Boyle's law is, let's say you are at the ocean, you're underwater, and then you breathe out the bubbles that is inside your lung. The bubbles at the low point or the moment it is released, it has a very small size. What happened here is that at this level, the pressure applied to the bubble is very high. But as the bubble moves towards the surface of the ocean, what you can see is that the bubbles get bigger and bigger. So in other words, we can say that the volume increases. Reason is because the pressure applied is much smaller. And this obey the law that we just stated earlier. The temperature on the ocean remain constant throughout, so they still obey this law. We don't take the depth of the ocean too much, where it is within 0 meter to 80 meter. If you go below 80 meter, then the temperature shifted. You can't follow your heat law any longer. As long as you kept between 0 to 80, it shouldn't be any problem for your gas bubble to experience Boyle's law. Now we're going to take a look at our Charles law. For the Charles law, the same definition as the Boyle's law, the only difference is for a fixed mass of an absolute gas, what happened here is that for Charles, the volume of gas is directly proportional to the temperature. Okay, in this definition you need to put the absolute, where pressure is kept constant. Here the formula for our Charles law, it is V1 over T1 equals to V2 over T2, where the volume is directly proportional to your temperature. That's why when we carry out the experiment, we can see that the graph form is something like this, where here we have our volume, and on the y-axis we have our temperature in degrees Celsius, and it starts somewhere in the middle. When we change the temperature from degrees Celsius to Kelvin, what happened is that we can see that it starts from 0, because the temperature in Kelvin is the absolute temperature. Here it can extend further to negative 273 degrees Celsius. This is the difference of the two graphs based on which temperature unit that you are using. Now, for Charles' law, what we'll see is that we can do simple experiments to show that Charles' law exists. For example, you can just use a normal balloon, a normal helium balloon. What happens in a normal helium balloon is that the balloon will rise upwards. As it moves from the ground position upwards, what you will see is that the temperature on the surface, as opposed to the atmosphere, the surface has a very higher temperature. It's a higher temperature compared to the atmosphere. So as the balloon moves upwards, you can see that the balloon experiences decrease in volume. And this decrease of volume is due to your Charles law. And finally, we have our Gay-Lussac law. This law is also known as the pressure law. In Gay-Lussac Law, it is defined as for a fixed mass of an absolute gas, what happened? The pressure is inversely proportional, is directly proportional to temperature where volume is kept constant. In the Gay-Lussac Law, what happened is that we can see the formula as P1 over T1 equals to P2 over T2, where your pressure is directly proportional to your temperature. When we carry out our experiment and we plot our graph, what we'll see is that the graph shows the same trend as it does for the Charles law, where the temperature is down below, the pressure is on this side, and you see that if the temperature is in degrees Celsius, it begins somewhere at the middle of the chart. But if we use the temperature at Kelvin, what happens is that you will have a perfectly lined graph where it starts from 0. For the Gay-Lussac law, the pressure and the temperature, we can see this in a simple experiment where a can be heated up first with its lid open. This causes the volume of air to remain constant throughout. The air will escape, and as the temperature increases, you cut off the heat, you seal the can, and you pour the can with cold water. So what happened? When you pour cold water to the can, the cold water will cause the temperature within the can to decrease. The gas inside the can will experience decrease in temperature, and it will start to crumple up due to the higher atmospheric pressure applied to the surface